How's your head? Are you in tune with this ytterbium ion, suspended, shooting it with lasers, all this kind of stuff? We've done all this work, but what can we do? All we've done so far is initialize the darn thing to 0 and measure it. You're not going to get much quantum computing power that way. So we're going to have to do something different. And we're going to apply gates to the qubit. And I've got a picture here of what's called a Bloch sphere. I'm going to show you this picture, and I want you to remember it because it says an awful lot about the states of qubits and how complicated they are. They're so complicated that we have to express them with complex numbers. Okay, here's a sphere. Now, it might look just like a circle, and it's really faded out over here because they're trying to do some shading. But this has 3 axes because it's 3-dimensional. A sphere is 3-dimensional, a circle is 2-dimensional. So let's think of the radius of this thing as the sum of the possible probabilities. If you take all the probabilities and add them together, they have to add up to 1. Let's use this to represent the 0 state, the vector 1, 0, and this down here to represent the 1 state. 0 here, 1 there. All right, class. What's the initial state? Well, the initial state is a 0 because we did this optical pumping and did all these various things, slowing down the oscillation rate of the ion and getting it all set up for this stuff, which was no easy task. Now what we're doing is we're applying a pulse, a very short pulse, and with a prescribed intensity. The intensity will show the speed at which this thing moves. Higher intensity, it moves faster. The duration tells us how far it's going to move. If we didn't have any phase difference, then this would just be right down here at the x-axis. But it's not. It's rotated around here. And if you think of this, this is kind of like the equator of a globe because it's halfway in between the 0 and the 1 state. So this phase is kind of like the longitude of that globe. Another thing to add here is that this would be, this state over here shown by the red X is a superposition between 0 and 1. If we measure this, it's going to end up right back at either 0 or 1. It'll collapse the wave function to be either one of those. But we have at this point, we have a 50-50 chance of being 0 or 1. How do we accomplish this? Our goal, it's called a Hadamard gate. Who knows where the name Hadamard came from? And really, at this point, who cares? What we want to do is put the qubit in superposition. That's halfway between 0 and 1. So here's what we're going to do is we're going to place this at a plus 90-degree phase from X. X would be 0 phase. And we want to put it, this looks like it seems like 90-degree phase would be right over here with the y-axis. So this picture is not really a 90-degree phase shift. It's more like a 45-degree phase shift. If we did a 90, this little red X would be over here. And also, we want to be able to do a superposition state where it's over here at this point. So it rotates on this side of the x-axis. So let's look at the details of how to do that. What does the Hadamard gate do? The Hadamard gate can be represented in matrix form. Okay, let's look at that. Does that make any sense? Right now, that's probably not too easy to understand. Here's another way to look at it, is that the 0 or 1-0 gate accomplishes this. And the 1-0 gate has 1 over square root of 2, 0 plus 1, and notice this is a quantity squared. There's parentheses around that. So why 1 over square root of 2? Well, remember, these things have to add up to 1. So if you square this, the squares of them have to add up to 1. So the square of this is going to be 1/2. So 1/2 plus 1/2, there it gets you 1. Now down here we've got a 1, which is it maps a 1 to this minus state. Here we're mapping a 0 to a plus state and a 1 to a minus state. And the minus state is equal to 1 over the square root of 2, 0 minus 1. And then notice here this minus down here. So the minus comes from this matrix as we can look at it. And I guess the easier way to think about it is the 0 is a 1, 0, and the 1 is a 0, 1. So it picks up the minus sign, whereas it doesn't pick up the minus sign when we're using the 0. That may have been a little too confusing. Now, how do we do this with the laser? Let's cycle down through here and see if we can find something specific about the laser. What we want to do is a 90-degree pulse. Now this is right here is supposed to be the pi symbol. The rendering here didn't come out right. It's supposed to be pi over 2 pulse. That'll give us a plus 90 degrees for this particular gate. And let's see if there's some details down here that we can use. 90 degrees is the same as pi over 2, if you remember your geometry course. And this is the Rabi frequency. This is the speed with which that thing moves. And this is the duration of the pulse, that little t thing there. So if we set our laser up correctly, this will apply the Hadamard gate to no matter what state is there, either a 0 or a 1, and it'll put it in a superposition state, which is cool because one of the very first applications is to use a Hadamard gate and to test the output of the Hadamard gate. The Hadamard gate is a superposition, so you'll get a 50% result of 0, a 50% result of 1. And that shows that we're actually measuring the superposition state, and it also shows that the wave function collapses into either 0 or 1. You can never come up with the measurement of this thing. You'll never be able to measure what it is, but you can know that that state is there. And that state can be used for entanglement. Entanglement between qubits. We're only working with 1 qubit, so we should have this foundation fixed in our heads, the Hadamard gate, and we'll be ready for multi-qubit systems. This is enough for now, though.